In the previous video, we talked about a cost function for the neural network. In this video, let's start to talk about an algorithm for trying to minimize the cost function. In particular, we'll talk about the backpropagation algorithm. Here's the cost function that we wrote down in the previous video. What we'd like to do is try to find parameters theta to try to minimize j of theta. In order to use either gradient descent or one of the advanced optimization algorithms, what we need to do, therefore, is to write code that takes as input the parameters theta and computes j of theta and these partial derivative terms. Remember that the parameters of the neural network are these things: theta superscript L subscript ij, that's a real number, and so these are the partial derivative terms we need to compute. In order to compute the cost function j of theta, we just use this formula up here. And so what I want to do for most of this video is focus on talking about how we can compute these partial derivative terms. Let's start by talking about the case of when we have only one training example. So imagine, if you will, that our entire training set comprises only one training example, which is a pair xy. I'm not going to write x1, y1, just write out one training example as xy. And let's step through the sequence of calculations we would do with this one training example. The first thing we do is we apply forward propagation in order to compute what our hypothesis actually outputs given this input x. Concretely, recall that A1 is the activation values of this first layer, that is the input layer, so we're going to set that to x. And then we're going to compute Z2 equals theta1A1 and A2 equals G, the sigmoid activation function applied to Z2, and this would give us our activations for the first hidden layer, that is for layer 2 of the network. And we also add those bias terms. Next, we apply two more steps of this forward propagation to compute A3 and A4, which is also the output of our hypothesis h of x. So this is our vectorized implementation of forward propagation, and it allows us to compute the activation values for all of the neurons in our neural network. Next, in order to compute the derivatives, we're going to use an algorithm called backpropagation. The intuition of the backpropagation algorithm is that for each node, we're going to compute the term delta superscript L subscript j that's going to somehow represent the error of node j in layer L. So recall that A superscript L subscript j, that's the activation of the jth unit in layer L. And so this delta term is in some sense going to capture our error in the activation of that node, or sort of how we might wish the activation of that node were slightly different. Concretely, taking the example neural network that we have on the right, which has 4 layers, and so capital L is equal to 4. For each output unit, we're going to compute this delta term. So delta for the jth unit in the 4th layer is equal to just the activation of that unit minus what was the actual value observed in our training example. So this term here can also be written h of x subscript j, right? So this delta term is just the difference between what our hypothesis outputs and what was the value of y in our training set, where this y subscript j is the jth element of the vector value y in our labeled training set. And by the way, if you think of delta, a, and y as vectors, then you can also take this and come up with a vectorized implementation of it, which is just delta 4 gets set as a4 minus y, where here each of these, delta 4, a4, and y, each of these is a vector whose dimension is equal to the number of output units in our network. So we've now computed the error terms delta 4 for our network. What we do next is compute the delta terms for the earlier layers in our network. Here's the formula for computing delta 3. Delta 3 is equal to theta 3 transpose times delta 4, and this dot times, this is the element-wise multiplication operation that we know from MATLAB. So delta 3 transpose delta 4, that's a vector, g prime z3, that's also a vector, and so dot times is an element-wise multiplication between these two vectors. This term g prime of z3, that formally is actually the derivative of the activation function g evaluated at the input values given by z3. If you know calculus, you can try to work it out yourself and see if you can simplify it to the same answer that I get. But I'll just tell you pragmatically what that means. What you do to compute this g prime, these derivative terms, is just a3 dot times 1 minus a3, where a3 is the vector of activations, 1 is the vector of ones, and a3 is again the activation, the vector of activation values for that layer. Next, you apply a similar formula to compute delta 2, where again that can be computed using a similar formula, only now is a2, like so. And I didn't prove it here, but you can actually, it's possible to prove if you know calculus that this expression is equal to mathematically the derivative of the g function, of the activation function, which I'm denoting by g prime. And finally, that's it. And there is no delta 1 term, because the first layer corresponds to the input layer, and that's just the features we observed in our training set. So that doesn't have any error associated with it. It's not like, we don't really want to try to change those values. And so we have delta terms only for layers 2, 3, and 4 in this example. The name backpropagation comes from the fact that we start by computing the delta term for the output layer, and then we go back a layer and compute the delta terms for the third hidden layer, and then we go back another step to compute delta 2. And so we're sort of backpropagating the errors from the output layer to layer 3 to layer 2, hence the name backpropagation. Finally, the derivation is surprisingly complicated and surprisingly involved, but if you just do these few steps of computation, it's possible to prove via, frankly, somewhat complicated mathematical proof. It's possible to prove that if you ignore regularization, then the partial derivative terms you want are exactly given by the activations and these delta terms. This is ignoring lambda, or alternatively, if the regularization term lambda were equal to 0. We'll fix this detail later about the regularization term. But so by performing backpropagation and computing these delta terms, you can, pretty quickly compute these partial derivative terms for all of your parameters. So this is a lot of detail. Let's take everything and put it all together to talk about how to implement backpropagation to compute derivatives with respect to your parameters, and for the case of when we have a large training set, not just a training set of one example. Here's what we do. Suppose we have a training set of m examples like that shown here. The first thing we're going to do is we're going to set these delta L subscript ij. So this triangle symbol, that's actually the capital Greek alphabet delta. The symbol we had on the previous slide was the lowercase delta. So the triangle is capital delta. We're going to set this equal to 0 for all values of Lij. Eventually, this capital delta Lij will be used to compute the partial derivative term, partial derivative with respect to theta Lij of j of theta. So as we'll see in a second, these deltas are going to be used as accumulators that will slowly add things to in order to compute these partial derivatives. Next, we're going to loop through our training set. So we'll say for I equals 1 through m. And so for the ith iteration, we're going to be working with the training example xi, yi. So the first thing we're going to do is set a1, which is the activations of the input layer, set that to be equal to xi, that is the inputs for our ith training example. And then we're going to perform forward propagation to compute the activations for layer 2, layer 3, and so on up to the final layer, layer capital L. Next, we're going to use the output label yi from the specific example that we're looking at to compute the error term delta L for the output layer. So delta L is what a hypothesis output minus what the target label was. And then we're going to use the backpropagation algorithm to compute delta L minus 1, delta L minus 2, and so on down to delta 2. And once again, there is no delta 1 because we don't associate an error term with the input layer. And finally, we're going to use these capital delta terms to accumulate these partial derivative terms that we wrote down on the previous slide. And by the way, if you look at this expression, it's possible to vectorize this too. Concretely, if you think of delta ij as a matrix indexed by subscript ij, then if delta L is a matrix, you can rewrite this as delta L gets updated as delta L plus lowercase delta L plus 1 times A L transpose. So that's a vectorized implementation of this that automatically does this update for all values of I and j. Finally, after executing the body of the for loop, we then go outside the for loop and we compute the following. We compute capital D as follows. And we have two separate cases for j equals 0 and j not equals 0. The case of j equals 0 corresponds to the bias term. So when j equals 0, that's why we're missing this extra regularization term. Finally, while the formal proof is pretty complicated, what you can show is that once you've computed these d terms, that is exactly the partial derivative of the cost function with respect to each of your parameters. And so you can use those in either gradient descent or in one of the advanced optimization algorithms. So that's the backpropagation algorithm and how you compute derivatives of your cost function for a neural network. I know this looks like it was a lot of details and this was a lot of steps strung together, but both in the programming assignments right out and later in this video, we'll give you a summary of this so that you can have all the pieces of the algorithm together so that you know exactly what you need to implement if you want to implement backpropagation to compute the derivatives of your neural network's cost function with respect to its parameters.